Okay, Assalamualaikum and good morning, everyone. Okay, welcome to our class today. I hope my internet connection will be all right until I finish this video. Okay, let me stop my camera first. Okay, can you see my slide here? Nampak slide tak?
Yes.
Okay, in the last couple of weeks, we have learned the types of dislocation, right? Okay, how many types of dislocation that you still remember? Ada berapa jenis dislocation that we have? If you still remember. How many types? Anyone can share your thought? Okay, first we have edge dislocation, right? And then we have a screw dislocation. And this is the symbol of edge dislocation. And this is the symbol for a screw dislocation. Okay, if you look at the picture here, well, what does this dark line represent? Okay, if you look at this picture, okay, what does this dark line represent? Okay, Anis, do you know? Atau maybe Marwan boleh jawab? Or anyone, what does this dark line represent? If you look at the picture here, ada siapa-siapa tak boleh jawab? What is this? What is this dark line? Okay, ada yang tahu tak? Anyone? Okay, so this dark line represent dislocation, right? Okay, if you look at this dark line, all this dark line, it represent dislocation. Okay, like what I have mentioned many times before, dislocation is what we call as a line defect. Okay, dislocation is a line defect. Okay, we call it line defect due to the reason that they do appear as a line, like what we can see here. Okay, so that is the reason why we call it line defect, because it does appear as a line. Okay, understand? Do you understand? Boleh faham?
Boleh.
Boleh faham Okay, you kena respond sikit sebab saya tak sure you dengar ke tak ni. Takut saya punya internet connection problem. Okay. Okay, that is the reason why we call this as a line defect because it appears as a line. So this is what we call as a dislocation. And also this line, they propagate throughout the material along a different dislocation line. So what we can see, for example, in the figure here, is that when the line appear to be darker, the density of dislocation is very high. Okay, if you look at this picture here, if the line appear to be very darker, then we can see that the density of line is very high. Okay, we also discuss some of materials need to be dislocation free to properly function. What are they? What are some examples? Okay, some examples of material that need to be dislocation free, for example, like gallium arsenide, silicon carbide, and so on. So what is the purpose? What is the application of this material? Anyone still remember? What are the application of this material? we discussed about this sebelum cuti hari tu. Ada yang ingat tak? What are some application of this type of material?
Tak.
Tak ingat? Okay, you ada belajar semiconductor tak?
Belum lagi.
Belum lagi. Okay. This type of materials we use for semiconductor application because if you want to use a material in the fabrication of a semiconductor, we need that material to be dislocation free. Okay, so all these materials, they are dislocation free. So we can use this type of material for semiconductor application. Okay, so some materials, we need that material to have dislocation for specific type of application. And some materials, we need that material to be dislocation free to properly function. So you really need to know how and when we need to introduce defect in material. It all depends on the application, right? Okay, so we have discussed a classification of a defect according to their dimensionality. So we have a point defect and line defect. We have discussed all about this defect. Vacancy, interstitial, substitutional. Okay, at certain given finite temperature, there is a concentration of point defect that is thermodynamically stable. Thermodynamically stable. Okay, can you see my slide here? Nampak tak slide?
Nampak.
Okay. Okay, what does it mean by thermodynamically stable? Meaning that when there is a certain energy required to form this, there is a certain energy that required to form this, and by introducing a point defect, we increase the entropy. So we increase the entropy of the system, and we have to remember that all these are something that we call as a zero-dimensional defect. Okay, kita dah discuss pasal zero-dimensional defect. Ada tak? What does that mean by a zero-dimensional defect? Meaning that they are very localized. Okay, they are very localized. So if we talk about individual atom, and therefore the strain or the formation of the crystal around them is very small, because you can see here that this type of defect is very localized, involve only a single atom. Dia melibatkan cuma satu saja atom, okay, single atom. So the formation of the crystal around them is relatively small compared to dislocation. Okay, in contrast to a dislocation is it involves a large movement of atom. Okay, dislocation involves a large movement of atom. So we call it line defect due to the reason that they appear as a line, like what I have mentioned just now. So line defect, it will move or propagate throughout the material along a different dislocation line. So what you can see here in the figure here, okay, what you can see in the figure here is that the density of the dislocation is very high if the line appear to be darker. Okay, faham eh? So the dark line here represent a dislocation of materials. Dislocation density can be really high. And how do we know that the density is high? If the line appear to be darker, and then we can say that dislocation can be really high. Okay, what are dislocation? Do you still remember what is the definition of dislocation? Masih ingat tak? Definition of dislocation. Anyone boleh tolong tak? Kita punya ni rakam ke tak? Siapa-siapa boleh check? Kita punya lecture ni rakam tak?
Siapa?
Kita punya rakaman on tak?
Ada?
Okay. Okay, do you still remember what is the definition of dislocation? So this is the definition of dislocation. Dislocation, a line defect that exists in metal. So they are typically introduced into crystal during solidification of the material. Okay, during solidification. And also when we deform the materials permanently. When we deform the materials permanently. Example of deformation of material such as cold working. Okay, have you ever heard about this term, cold working? Dah dengar tak? Contoh cold working yang paling senang, we use a roller. Okay, let's say this is a material and we use roller. So we allow that material to pass this roller and it will change in shape. Dia jadi nipis. So this is what we call as a cold working. So dislocation, line defect that exists in metal. We have two types. We have edge and screw dislocation. So the symbol for dislocation, ni symbol dia macam ni. This is the symbol of dislocation. And the dislocation density in anneal metal is normally about 10 to the power of 6 per centimeter cube, centimeter squared. Okay, anneal mean a heated material. Right? So if you look here, this is the transmission electron microscopy image of edge dislocation. So we can see that the existence of lattice mismatch. Okay, if you look at this picture here, can you see the difference between here and here? What is the difference between these two? What can you see here? Apa yang you boleh nampak dekat figure ni? Saya zoom Okay, if you look at the picture here, what can you see? Okay, what can you see at the above region here? Apa yang you boleh nampak?
Dia dua jadi satu.
Dekat at the above region here, we have an extra line, kan? Betul kan? We have an extra line here. So this is what we call as a line defect. This is the lattice mismatch. Okay, we can see that we have an extra half plane here. Okay, we have an extra half plane here at the upper side. Okay, now we have amorphous versus crystalline material. So at the figure here, we can see that the differences between a crystalline and amorphous state. So this would be an example of a transmission. I think this one is a transmission electron micrograph of a structure that is composed of silicon and silicon oxide. Okay, dekat atas ni silicon oxide, and below here we have a silicon. So in the case of silicon, we can see that the atom position is periodically arranged. Okay, if you look at the picture here, we can see that for silicon, the atom is periodically arranged. Okay, how about this one? How about silicon oxide? Okay, if you look at the silicon oxide here, we lose that. Okay, if you look at the silicon oxide here we have what we call periodically arranged. Okay, for silicon here we have a periodically arranged, but for silicon oxide we lose that periodicity. But if you look closely at that image, we also notice that this particular structure, it is not a completely random. Okay, silicon oxide ni dia tak completely random. Dia ada juga susunan dia. If you look very closely, we can see that some local arrangement of atoms that reflect that this amorphous material. Okay, this amorphous material do have a short range order. Okay, so dia tak adalah completely random. It has some kind of arrangement that we call as a short range order. Okay, I think you already know about this. Slip, if you still remember, is we can define as a movement of a dislocation that cause the material to permanently or plastically deform. Okay. Okay, as the shear, if you look here, as the shear continue through the lattice, this is what we call as a lattice. The plane is moved all the way to the lattice until it emerges on the other side. Okay, until it emerges on the other side. And the plane on which the slip occur, what we call as a slip plane. Okay, slip plane. Okay, the slip plane is the plane on which the slip will occur, and the direction of the shear, what we call as a slip direction. And normally the angle here, kebiasaannya this angle is 45 degree. And the slip plane and direction are characteristic of a crystal structure of material. Okay, why do we call it slip? Okay, why do we call it slip? Ataupun in Malay we call it a gelinciran, because the atom it slip past each other, like what we can see in the figure here. They happen at a specific crystallographic plane. Happen at the specific crystallographic plane in a specific crystallographic direction. When I say they happen at the specific crystallographic plane, meaning that it happened at the highest density plane. Okay, for example, we have a FCC. We have a FCC. What is the full name of FCC? Ingat tak? FCC. Apa full name dia? We have a BCC, we have a FCC, we have a HCP, right? What is the full name of FCC? Apa nama penuh dia? Ada yang ingat tak? Okay, FCC, if you still remember, is the face centered cubic, yeah? Okay, like what I have mentioned before, slip happen at the highest density plane in the highest density direction. So for FCC or face-centered cubic, it is the most dense at this direction. So for FCC atom arrangement, dia paling pack sekali dekat sini lah, this type of direction. So slip will happen at this direction. So we can see that the plane will cut through the atom with the highest planar density plane. Okay, you all dah belajar kan what is FCC, BCC and HCP? Ada tak?
Dah.
Dah belajar? Ingat lagi tak? Do you still remember what is FCC, BCC and HCP? Belajar bila ni? Belajar SM1 SM1, ingat tak lagi?
Ingat. HCP tak tahulah.
Ingat sikit-sikit lah kan?
FCC dengan BCC lah.
Okay, so dekat table ni, if you look at this table, we can see that the slip system for BCC, FCC and HCP metal. So if you look at the information in the table here, from this information, I want you to figure out, okay, why does HCP metal is brittle compared to BCC and FCC? Why? Okay, kenapa HCP metal lagi rapuh or brittle compared to FCC and BCC? Why? This is something that we can relate to a slip system. Okay, you tengok dekat sini Okay, if you look at this value, can you give a reason why HCP is brittle compared to these two, FCC and BCC? Nampak tak number of a slip system here? What can you conclude if you look at this number? Kenapa HCP lagi brittle daripada FCC dengan BCC? Anyone? Can you share your opinion about this? Okay, ada tak yang boleh share your opinion ataupun you punya answer lah about this? Why do you think? Siapa tu?
Dia number
Anis
saya.
Okay, Anis, why?
Number of slip system untuk HCP tu dia lagi sikit.
Betul
Compare dengan FCC dengan BCC.
Okay, so if we have a less slip system, okay, if you look here, if we have a less slip system for HCC compared to BCC and FCC, what happened? Apa jadi tu Anis? What happened? Okay, what happened? Because we have a less slip system for HCP metal, So the movement of dislocation will be restricted. So that is the reason why BCC and FCC is more ductile compared to HCP. Okay, boleh you relate tak dengan slip system? Can you see the relation between the slip system and ductility? Boleh nampak tak dia punya hubung kait dia? Boleh tak? Anis, boleh tak nampak?
Apa tadi doktor kata?
Okay, because we have a less number of slip system here, so meaning that HCP is less ductile. Sebab okay, we define slip system as something that we can relate to a movement of a dislocation. So if we have a less number here, meaning that HCP, the dislocation, the movement of a dislocation for HCP is restricted. Betul? Betul tak? So
Betul.
as a result, HCP is less ductile than these two. Okay, faham Betul tak Anis?
Faham.
Faham So if we have a large number of slip system, meaning that the dislocation can move easily. So as a result, our material will become what? Material kita jadi apa? If we have a larger number of slip system. So we have ductile material lah. Sebab dislocation can move easily. But if we have a less number of slip system like what we have for HCP material here, then our material become brittle. So as we already know, metal deform along the closest pack direction on the closest pack slip plane, and this is what we call as a slip system. Slip system where the bonding were breaking and reforming in order for dislocation to move since the atom are closer together. So it is easier for bond to break and reform in their closest pack direction. Okay, this is an example, okay, for FCC, like what I have mentioned before. So the most dense atomic packing for FCC is here at the 111 plane. So this is the most dense, yang paling padat sekali, the most dense atomic packing. And the highest linear density is at this direction, 110. Slip direction 110 exhibit the highest linear density. And here we have a different variation of a 111 plane in FCC metal. Okay, all these are 111 plane in FCC. Just a quick review of what you have learned before. Ada pelajar tak pasal plane ni? 111 plane. Have you learned about this? Pernah belajar tak?
Pernah.
Ingat Now we talk about dislocation density. So dislocation density, we express it as a total dislocation length per unit volume, or equivalently the number of dislocation that intersect a unit area of a random section. So dislocation density unit here can be either millimeter per millimeter cube or 1 per millimeter squared, and can be as low as 0 to the power of 3 millimeter squared. For ceramic, can be as low as this value. So if we look at the figure here, okay, this is how we calculate the dislocation density. For example, we have a total length of a dislocation. Okay, we have a total length. You nampak garis-garis ni. We measure all the length. We divide by the volume of this cube. So if this is the way we calculate dislocation density, then the unit will be millimeter per millimeter cube, right? Okay, this is the example of a cold work that I have mentioned just now. Okay, for a well annealed crystal, for a metal that we heat at a certain temperature, the value of a dislocation density lebih kurang 10 kuasa 10 per millimeter cube. Okay, when we apply a cold work to that material, okay, when we apply this process, this is a light cold work. When we apply a light cold work to that particular material, then the value of density can increase by the order of 2. Lebih kurang 10 kuasa 12. Bila kita apply a light cold work. But when we apply a heavy cold work to that particular material, then the dislocation density can increase up to dia meningkat sampai 1,000,000 kali compared to a well annealed metal. So we can say that a plastic deformation increase dislocation density. Faham? So any question so far? Ada soalan? Kalau tak ada, we discuss a bit. This is the continuation from the previous slide. Okay, dislocation density, the length of a dislocation per unit volume. So we measure the length, kita ukur panjang dislocation tu, all this dislocation, we measure the length and divided by the volume of this cube. So this is the unit. But another way, if we want to measure dislocation density, we can calculate the number of intersection. Okay, let's say we have a 2 dislocation here. Okay, we measure this intersection. So for example, here we have a 2 intersection divided by the area, and the value will be 1 over millimeter squared. Faham? Between these two, boleh beza tak? Can you differentiate between these two ways of how we calculate density of a dislocation? Nampak beza tak antara ini dengan ni? Nampak tak beza antara dua cara kita nak kira density ni? This one and this one. Okay, for this one, for the first method, we measure the length of a dislocation. But for this number two technique of dislocation density calculation, we measure what? Apa yang kita kira kat sini?
Area.
Kalau tengok sini kan, kita kira apa? Okay, let's say we have two line. Kita kira kat sini. What is this? We measure what? Tadi ada yang kata area. Area tu betul. Area betul. Area kat sini lah. Millimeter square ni. Tapi per area tu apa kita kira? Let's say we have a two dislocation here. Apa kita panggil ni? Intersection lah. Intersection of dislocation. Okay, let's say we have a three intersection per millimeter cube. So this is the density of dislocation. We have a three intersection per millimeter squared, not millimeter cube, millimeter squared. Faham eh? Okay, I think I can skip this. Okay, I think by now you already know the differences between edge and screw dislocation. Okay, Slip explained why the strength of metal is much lower than the value that we predict from the metallic bonding. So let's say if we had to break an iron bar by breaking all the bond along the cross section, then we will have to apply 1,000,000 pound square inch. But instead, we can deform the bar. We introduce a dislocation into that material by causing slip and probably only 10,000. We only need a 10,000 pound square inch. We only need a 10,000 square inch to break the iron bar. Okay. So this is the reason why slip is much lower. The strength of metal is much lower than the value that we predict from metallic bonding because we have a slip in that material. Okay, let's say we don't have slip in that material. So the material will become very strong that we require 1,000,000 pound square inch just to break all the bonding, along the cross section. But due to the existence of a slip in that material, we only required about 10,000 psi to break the iron bar. Okay, and also slip will provide ductility in metal. Let's say if we don't have a slip that exists in that metal, then that material or that metal will become very brittle. Okay, if a dislocation cannot move, so plastic deformation will not occur. So you have to remember ductility or malleability. Okay, ductility or malleability of material is due to the dislocation movement. All right. Okay, if you look at the animation here, okay, this is the model of a slip by the movement of edge dislocation. So we can see that the movement of a dislocation allow atoms to slide. Okay, kita tengok dekat atas ni. We can see that the movement of a dislocation allow atom to slide over each other at a low stress that we call as a glide. Okay, glide or slip. Kalau you tengok dekat animation below here, this movement is very similar to movement of what? Ni apa ni? Apa nampak? You nampak apa kat sini ni? Dekat gambar bawah ni apa you nampak? Okay, you nampak apa kat bawah ni? Gambar apa ni? What is this? Ni ulat beluncas, beluncas ke? Ataupun ulat bulu, caterpillar. So we can use the movement of caterpillar as an analogy to the movement of edge dislocation. Okay, I will just go through this one quickly. Edge dislocation, we have two types of movement. We have a conservative ataupun glide. Glide like this one. This is what we call as a glide. Okay, and then we have another type of movement, edge dislocation, that is a climb. Okay, kalau climb ni, for climb movement, it will move. The movement of dislocation will be perpendicular to the slip plane. So if you look here, the dislocation, it moves upward. Okay, this occurs when dislocation absorb or emit a vacancy. Okay, this happen. This type of movement, it usually happen at a high temperature. It is much easy at a high temperature. And this one, this type of movement, it is what we call, it is a very slow process. It doesn't produce a large amount of deformation. It acts as a mechanism for dislocation to move around an obstacle. Okay. Okay, for this one, for this type of movement, dislocation by applied shear, and it is not particularly sensitive for this type of edge dislocation. But this type of dislocation, where we can see that the dislocation moving upward, it happened at a high temperature. Occurs when dislocation absorb or emit vacancies, and it is much easier at a high temperature. And it is also a very slow process. Okay. Okay, for screw dislocation, the slip direction is parallel to the dislocation line. And for edge dislocation, slip direction is perpendicular to the dislocation line. Okay, we do some review here. Deformation of metal, plastic deformation is permanent. It involves breaking and reforming of bonding and includes the motion of what? Ada yang boleh jawab tak? Okay, plastic deformation is permanent. Involve a breaking and reforming bond and includes the motion of what?
Dislocation.
Dislocation. And edge dislocation travel in direction. Direction in what type of direction? To applied force.
Parallel.
Apa jawapan? Parallel.
Parallel.
Screw dislocation travel in direction what? To applied force.
Perpendicular.
Perpendicular. So we can see that for edge dislocation, it is parallel. For screw dislocation, it is perpendicular. Okay, edge dislocation travel in direction parallel to the applied force, like what we can see here. On the other hand, for screw dislocation, it is perpendicular. I think I just skip this one. Okay, now we talk a bit about the Berger vector. This is the last subchapter in this chapter. So we can define a Berger vector as a magnitude and direction of the lattice distortion resulting from a dislocation in the crystal lattice. So the keyword here, so the keyword here is lattice distortion. So the keyword for a Berger vector is we can relate it to a lattice distortion. Okay, if you look at the picture here, okay, let's say that we have a perfect crystal and we move around this circuit. Okay, this is what we call as a circuit. Okay, if we start from here, okay, let's say we move 1, 2, 3. We move 3 steps to the right, and we move 1, 2, 3, 4 step downward, and then we move again 1, 2, 3 step to the left, and we move again 1, 2, 3, 4, and then what can you conclude here? When we move around this circuit, our starting point is similar to our endpoint, right? So this is what we call as a perfect crystal. There is no distortion in lattice crystal. When the crystal is perfect, we end at the exactly same position as we started. Okay, let's say that we have extra plane here. Okay, katalah kita ada extra plane here on the top of our structure. So what we see that the end position, let's say we start from here, 1, 2, 3, 4, we move 4 step, then we move 1, 2, 3, 4 step downward, 1, 2, 3 here. Okay, kita start dari sini we start from here 1, 2, 3. We start from here 1, 2, 3 step to the right, and then we move 1, 2, 3, 4 step downward, and then because of the existence of this extra plane, our endpoint will be here. Okay, the end position is not the same as the starting point. So the extra distance here is what we call as a Berger vector. Okay. So we have our dislocation line, we have our slip plane, and we also see that the Berger vector is a perpendicular to the line to the line of a dislocation. Faham Boleh faham? Faham tak pasal Berger vector? Boleh faham Okay, if you look at the, kalau kita tengok daripada depan, okay, if we look here at the figure here, we look this figure from the front, kita tengok daripada depan, but if we look from the side, we can see that the dislocation, it enter deep into the crystal. Dia ada lagi kat belakang-belakang ni. Dia bukan satu ni je. Okay, kalau if you look from this side, it enter deep into the crystal. So all this bunch of atom, a huge number of atom is what we call as a slip plane. Okay, dia bukan ni je, bukan dekat depan ni je. If you look from this side, it enter deep into the crystal. We have a whole number of atoms involved. So this one twinning, I think I already shared the YouTube video with you. Okay, before we stop our class, just a quick review. Can you differentiate? Boleh awak bezakan tak antara single crystal and polycrystal. Can you differentiate between these two? Boleh tak bezakan antara single crystal dengan polycrystal? Ada yang nak try tak? How we differentiate between single crystal and polycrystal? Okay, saya bagi satu for single crystal, we have a periodic and repeated arrangement of atom is perfect throughout the material. How about polycrystal? Anyone want to try? Kalau single crystal, kita ada periodic and repeated arrangement of atom. We have a perfect arrangement of atom throughout the material. How about polycrystal? Kalau polycrystal macam mana? Anyone want to try? Fifi mungkin boleh jawab. Fifi Alfiani. How we differentiate between single crystal and polycrystalline. Ataupun Marwan ke? Ada tak nak cuba?
Dia periodic by across the each grain.
Yang itu untuk apa? Untuk single crystal ke polycrystal? Poly. Siapa tu? Fifi ke? Siapa jawab tadi?
Saya Anis
Amanina. Anis Nur Amanina. Okay, sebab Anis jawab tadi, nanti kuis saya tambah 2 markah. Anis Nur Amanina kan?
Ya saya.
Okay. Okay, untuk single crystal, okay, for single crystal, we have a periodic arrangement of atom throughout the material. For polycrystal, okay, we have a grain here. We have many grain, composed of many grain, many small crystal of grain. Okay, and each crystal they have its own arrangement. So, like the name, polycrystal consists of many crystal region. Single crystal consists of only one single region. So that is how we differentiate between single crystal and polycrystal. Okay, as a conclusion for this chapter, it can be said that the existence of a dislocation required to cause deformation at a much lower amount of stress. Okay, for perfect crystal, if that ever existed, it will require a very high stress to cause deformation. Why? Kenapa? Why we require a very high stress to cause deformation for a perfect crystal? Okay, you answer that. You jawab sendiri. You cuba fahamkan from my note and try to answer this question. Why we require a very high stress to cause deformation for perfect crystal? I think I already covered this, but if you still can't answer this, you rewatch again my video and try to understand the concept of a dislocation and how it affects the property of material. Okay, in terms of a strength, which arrangement, single crystal or polycrystalline material will yield a higher strength? So there is no answer. There is no definite answer for this question. Some references say that a single crystal is stronger, while others say otherwise. But for the sake of simplicity, we can conclude that a single crystal is much stronger than polycrystalline material, because we don't have a dislocation, and that make single crystal material to become more stronger compared to polycrystalline material. But polycrystalline material will be more ductile compared to single crystal material. Okay, so, some review before we end our class here. A slip system is the combination of a slip plane and slip direction is, so this is what we call as a slip system, a combination of a slip plane and slip direction. Okay, if I ask you, do all metal have the same slip system? The answer is no, because for most metal, the slip system consists of the most closely packed crystallographic plane, and within that plane, the most closely packed direction. Plane and direction will vary from one crystal structure to another. And what is the significance of the slip system? So slip system is very significant because it will, this is the direction in which the atom are most closely packed. Slip plane and slip direction constitute of a slip system. A critical resolve shear stress required when we want to initiate a slip. And a slip system is very important in the case of a deformation mechanism in crystal, and how the material will react when we apply forces to them. So that is the significance of a slip system. It will determine how the properties of the material, how it reacts when you apply forces. Some material will become ductile. Some material are ductile, some material are brittle. It all goes back to the existence of a slip system in that particular material. So I think I stop here. Any question so far? Ada soalan ke? Ada apa-apa nak tanya? Ada soalan?
Tak ada, Doktor.
Okay. Okay, that's all. Thank you. Nanti bagi tahu kawan-kawan untuk tengok rakaman video. Okay, thank you all.
Thank you, Doktor.
Jumpa lagi. Kalau ada soalan boleh tanya dalam grup
Okay,
WhatsApp.
thank you, Doktor.
Okay, sama.